You hear that? The hum right there? That's electrical power being transformed into a mechanical force at over 3,000 RPM. We're playing with belts and pulleys today. Speed traded for torque, torque traded for speed. And by the end of this video, you have the knowledge to take a pile of parts and build this drive with your very own hands.
Welcome to Module 4, Introductions to V-Bone Drives. I'm John Coddington. I've been breaking things and fixing things for almost 30 years, so buckle up. We're going to have some fun. Here's what we're going to cover today. A pulley ratio math, shaft speed, torque calculations, full installation and alignment of the V-belt drive, tension of the belt according to the manufacturer's specs, and then we're going to run it under load and see what that data tells us. Why? Because V-belts are everywhere. Conveyor systems, HVAC compressors, machine tools, agricultural equipment. If you work in manufacturing or maintenance, you're going to work on these. So let's get to it. Before we touch anything on this whole entire machine, we need to talk about safety. I'm not going to read you some list like a flight attendant. Just know that I mentioned these CCAMs for a reason. And that reason is so you can keep all your fingers, your toes, and your eyesight the rest of your career. So what are we talking about? Loose clothing? That's a no-go. Sleeves? Roll them up. Gloves? Not around rotating machinery. That's not good. Jewelry? You don't want anything loose, anything that get caught in pieces of machinery. Even long hair. You have long hair? Tuck it up, put it away. Other than that, shoes? You want to keep those toes? So I suggest wearing shoes that are practical and tactical.
All right, lockout, tagout. It's not a rule, it's the law. Every maintenance tech, student, every person working near this machinery should put their own personal lock on. So here's how we're going to do it. I'm going to take my personal lock, put it on, tag with personal information on it so people know who locked it out. Take the key, comes with me. Then, most importantly, start it. It didn't start? Good. That's the whole idea. Nobody can accidentally start this machine while you're working on it. All right, with our safety talk over, we can now look at the parts that we have to build this drive. I got everything laid out, so let's take a peek. I have 2 pillow block bearings complete with a 1-inch hole. I have 4, count them, 1, 2, 3, 4 standoffs for those pillow block bearings. They are 2¼ inch long. We have this shaft that comes in our kit. It's the one all the way in the back. It has a 1-inch center that'll go through these pillow block bearings. All right, we got our belt. Our belt is a V-belt. It's called a V-belt because it has a V shape into it to fit inside the V-shaped channel on your sheaves. All right. Speaking of sheaves, look what we got. We got 2 sheaves. One is 2 inches. Right. The other one is 4. All right, we have some bolts. This is a 3/8 by 16 by 4½ inches long bolt. We also have a 3/8 by 1.5 inches long. And we have some, looks like 5/16 by 1 inch, and all their appropriate hardware. Measuring bolts, you measure the threaded part. Okay, it's time to mount the adjustable motor base. If you look at your diagram, you'll see that there's a lot of different bolt patterns all over this base plate. The ones we're going to use for this adjustable motor base is here and here. Okay, they're two small slotted holes on either side. So slide that guy in place. Instructions tell us that we're going to use our 3/8 by 16 bolts by 1.5 inches long. As always, we're going to put the washer on. And then when we go and we put the rest of them together, we are going to put the washer and then the lock washer underneath. We're just going hand tight. We're not going crazy just yet, and you'll see why. It's looking good so far. So what I'm looking for now is a soft foot. Soft foot is when what you're mounting to your base doesn't quite sit flush, and then if you might get a rock to it. This one seems pretty solid. I can't get my my feeler gauges under any of the feet, so we're doing okay. There's no wobble, no soft foot. So it's time to tighten it all the way down. Tighten it down. One thing you don't want to happen while you're putting your motors and your bases together is once it's all together, you put tension on that V-belt, it's going to want to shift this, cock it. And you don't want that to happen. That's why we really need to tighten this down. So as I'm tightening these down, right to tight, left loose. All right, I'm going to get it close. Okay, grab the end of the wrench and pull it. I'm using the end of the wrench because you get more leverage at the end of the wrench. You paid for the whole wrench, use the whole wrench. So now we're going to cross over, tighten it over here. The reason you cross when you tighten down your motors is so it's to prevent warping in the frame or the base of the motor or whatever you're mounted to. Lastly, okay, so now it's time to put that motor on the base. All right. We are going to use our 5/16 by 1 inch bolts. I'm going to go ahead and bring them through the bottom. All right, I have a washer. Now I have another washer, lock washer, nut. Just finger tight for now. To make getting our inch bolts into the frame much easier, we're going to just go ahead and take this nice adjustable base, loosen that nut right up, and look, now I got all this space underneath it. I don't want it to close down on me like an alligator mouth, so I'm going to go ahead and raise this bottom nut up till it holds that motor frame up. That makes it a lot easier for me to squeeze in, get my 1.5 inch bolt and washer, lock nut, and nut on. Now let's check for softwood. You might get something wobbly. Uh-oh, that's not good. With those bolts tightened down, we shouldn't have a wobble. Now I loosened it up just so you could see what a wobble would look like. But if you had softwood, you would have to measure for it. Okay? And then, after you measure for it, you'd have to get out your shims, shim the motor properly to eliminate that soft foot. All right, with this motor snug down pretty good, we're not gorilla tightening it down. Once it's snug down okay, it's time to check for level. So, with that motor off, we got quite the bubble difference. Time to get out our feeler gauges. We're going to slip it underneath the front here. And it's just about right. On this, I have a difference of 0.13. Now we need to measure this distance. That distance is approximately 2 inches. We then need to measure our bolt distance. So I have between here, center to center, 3 inches. So let's do it. Let's figure out what shim thickness we're going to need. All right, there's an equation we're going to use for our shim thickness. And what we're going to do is we're going to take our feeler gauge measurement, and then we're going to multiply it by the distance between bolts on the motor divided by that distance of the level on the shaft. So now what does that equal? Thickness equals 0.13 is what we measured, multiplied by 3 inches distance between the bolts on our motor frame. 2 inches is about what we measured on the shaft. Shim thickness is going to equal 0.195, or roughly 2/10 of an inch. So we're going to grab our shims, put in those, and tighten this motor down. It's time to start assembling the other shaft. So I'm going to start with the 2 pillow block bearings. Something I want you to know, trick, is I swear a lot of people mess up. These bearings have set screws and they can't go into here and slide on the shaft. They'll mar the shaft. So you want to make sure that it's nice and clear and that those are recessed before you put them on. Ours are. Alright, so I'm going to go ahead and I'm going to assemble this with these on the inside of the shaft. They should slide in and out relatively nice. Okay, it's time to mount our bearings. There's a lot of holes on this plate. We're going to use these 4. So take our standoffs, put them on. This is still loose, right? Drop that in. Lastly, drop that in. Now we're going to want it somewhat straight, somewhat level with each other. And we're going to go ahead and put our hardware on. Washer, lock washer, nut. Again, we're not tightening anything over. Time to check our level on our shaft. I go ahead and I put it on. I see that this bubble on my shaft, the end of the shaft needs to be raised up in order to center that bubble. So I'm going to go ahead and take my feeler gauges and start feeling in here. And I'm going to keep checking until I find just the right one to make the bubble exactly where I want it to be, which is this one right here, which is a 0.008. I don't know if you can see that. I was putting it in right at the end in order to get that. All right. So if I were to measure with my ruler how far over, I have it over about an inch in order to make that perfect bubble. About an inch. Okay. So an inch here. Then we have to measure our distance here, which we have at 2 1/4. So let's go ahead and calculate the shim thickness for that shaft assembly. Shim thickness is going to be equal to that feeler gauge measurement multiplied by bolt distance on the bearings divided by that shaft measurement with the level on it. So what were those numbers? We had 0.008 is what we measured with our feeler gauges, multiplied by 2 1/4 inches. And then we only used 1 inch there. So when we do this math, our new shim thickness is going to equal 0.018. Let's just say 0.02, 2/100ths of an inch. That is the new thickness of the shims that we are going to use. All right, so after I did my calculations, I figured out that I needed these 2 shims. I loosen these up, slide them right underneath those pillows. Okay. Straighten that out a little bit. All right, if I'm just curious, That looks perfect, but we're going to go ahead and tighten these things down. It's time to put on our sheaves. We have a 2-inch sheave. That's the inside. And a 4-inch sheave. All right. According to our prints, we are going to put the 4-inch sheave and take this and put it on there. Now, here's the big mistake. A lot of times, you take these, see this keyway here? This key seat, you need to make sure that this set screw does not protrude into the key seat. So let's take a peek at this one, shall we? I can see this right here, all right? And if I put this in here, you can kind of notice that key pushes into there. We need to back that out. Now I'm going to take my handy dandy Allen wrench, back it out to where it's completely clear, okay? So on this one, I need to make sure it's clear, and it is. Time to put in the key, all right? I have some keys here, some keyways. Now, what you need to do, a lot of people make this mistake, you got to make sure that the key fits in snugly. Hand tight, but not pressed in. You never want to have to hammer it. So we're going to just take this key, and we're going to see if this works, all right? I slide this in, and look at this. This is a lot of wobble. This key is really worn. Now that one, throw that one out. But this one here, let's see if this one works. Okay, I see it. It slides in, snug, and flush with the end. Wow, that is our key. So I'm going to go ahead and take it, and I'm going to line this key seat up with this keyway and slide it on. I want to make it flush with the end. Flush with the end. And then, where I can't feel it here, or where I feel it even here, and then I'm going to go ahead and tighten this down. All right. It's the key that holds this in place from slipping. This just keeps this from walking off. So you're just tightening this down enough to hold this in place. All right, it's time to put the 2-inch sheave on this motor. Just like we did on this pulley, we need to make sure that the set screw is recessed enough in the key seat. We need to take our key, make sure that it goes in. Okay. Nice. Not loose, but snug in there. We're going to take this key. It's keyed in there. All right. We're going to make it flush with the end right here. Okay. Tighten that down. Time to do the sheave alignment check. Okay. We don't want these sheaves to be doing something like this, or something like this, or this is straight and that one goes off to the side. So we need to make sure that these line up just perfect. We need to take this long, straight edge. Okay. I'm going to place the straight edge over this driven sheave, and I'm going to make sure it touches here and touches here, both sides of this sheave. Okay, and I'm going to put it across, and I'm going to pull this guy out until it lines up with that driven sheave. And I'm going to look, it needs to touch, when I'm done, it needs to touch here, 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 and here. But if I looked very closely, I could see that there is the ever slightest gap in here. In which case, in order to make this line up, I'm going to have to loosen these. Okay, just a little bit. Okay. And then, check it again. Touching here, touching here. And what do I have? It's off just a smidge. I have to just do the slightest tap. Okay. And now, let's see if I line up. I'm going to touch there to there, bring it across. And what do I have? Let's bring it in. It touches here, 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 and here equally. Let's just bring it in. Right, perfect, right there. So, with that in place, we are now going to start locking things down. Double check it. Looks good. I'm going to go ahead and slide it across this biggest one and watch it just touch that. Just slide on, and it is perfect. Perfectly lined up. All right, so this belt, it's going to go on last. All right. It is a V-shaped belt. It is an A37. Okay. A is the width. 37. Right. The 37 is the inside length. Okay. So I'm going to take it on and I'm going to put it on here. Uh-oh. I can't reach. That's why I have an adjustable base. Look at that. Slides right on. So now it's time to tighten these bolts down. I'm going to just kind of get a feel of it. All right. You can kind of see how much deflection. Belt tension is not guesswork. All right. If it's too loose, what's going to happen is the belt will slip. It'll start to get really hot and it'll wear out really fast. Okay. If you tighten it too tight, then what you're going to do is you're going to start to destroy the bearings. They're going to start to go, or you're going to start breaking this belt up sooner than later. Okay. So what we need to do is look at the specs for this belt and decide how much deflection that should have using our belt tensioner tool. All right, let's talk about tension. We need to know how much tension to put on this belt and how to figure that out. Well, there's 3 ways to figure it out. You can use your hand to test it. That's one common way to test it. It is not the most accurate way to test it. If you did use your hand, the most basic way is to just kind of strike the belt with your hand. If it feels alive and springy, then it's okay. If it feels dead, then it's too loose. If it feels too taut, then, or no give at all, it's too tight. But it's not the most accurate way to tell. And also, if you have like a wedge belt, this is not the way to do it. So we're not going to do it that way. Another way you could do it is with a spring scale. And that's very similar to what we're going to be doing. We're going to actually be using a tension tester. Because I don't have the spring scale, this is what I'm going to show you how to use. Okay? So, these are the 3 ways that we have. But first, we need to figure out the big question of how much tension. Okay? Well, belt manufacturers will give you a chart. If you look on your sheet, you'll probably find a chart somewhat like this. All right? They'll issue this sheet, and then you should be able to look at it and figure out what the proper tension is. I have a blown up one of the section we need right here. Okay? So, on this chart, you're going to see different things. You might see what kind of belt it is. Ours is an A37. A37. So with an A37 belt that's solid and not notched, right? An X would be notched. So with a belt that's just an A37, and I know that if I were to measure or look at my drive, I have a small sheave that's 2 inches, 2 inch, and I have a larger sheave that's 4 inch. And I have this A37 belt that's going around them both. Okay. Inch. So, I know with this, I have a 2 inch sheave. That is the smaller sheave diameter. That's the one I want. So I'm going A here. And it tells me that on a new belt, my minimal deflection force is 2.6 pounds. Okay. On a used belt, my minimal deflection is 1.8 pounds. Okay. Well, fine and dandy. That's the minimal. Do you have to hit that exact? No. What's the maximum? Well, your each deflection in pounds is allowed to go up to 1.5 times. So if I were to multiply each one by 1.5, I would get 3.9 pounds here, and I would get 2.7 pounds here. What does that mean? It means on a new belt, anywhere between 2.6 and 3.9 pounds is good. On an old belt, anywhere between 1.8 and 2.7 pounds is acceptable. Okay? Awesome. This is not the only thing we need to know. We know how much tension, great, but how do we use this tool? Well, in order to use this tool, you need another measurement. We need to measure from here to here. Okay? If I were to measure from the center of the shaft to the center of the shaft, on our current example, I get 15 inches. Great. What do I do with that number? Well, I take that 15 inches, okay, and I'm allowed per inch 1/64 of an inch deflection per inch of this distance. So if I multiply by 15 by 1/64, I am allowed, let's see, 0.234, that's roughly a 1/4 inch. We'll say a 1/4 inch deflection. Okay? What do I mean by a 1/4 inch deflection? Well, what I'm saying is when I push down on this, okay, 1/4 an inch, I want to see on a new belt somewhere between 2.6 and 3.9 pounds in pressure. Let's see how that works. I'm going to take this plunger, all right, and I want it to, I'm going to go ahead and put it near that. We said it was 0.23 inches or 1/4 inch, right? So if I look here, I can see that 1 inch. That's 3/4, that's half, that's 1/4 down there. So I need that much deflection on this, okay? So I'm going to take my plunger and put that all the way down in there, okay? So with this marked at our 1/4 inch, which is all we're allowed, and this all the way down, we're ready to use our tool. What we do is we line our straight edge up, okay, just like we did, and then we're going to take this tool and I'm going to push down on this plunger until this O-ring lines up with the bottom of that ruler, okay? So I'm going to put this here again, push down on the top until that lines up with there, and then I look here. What do I have? All right. I have 3 pounds. So we got it all together. Great job if you ask me, okay? We need to put the guards on. I don't care if we're running it for 30 seconds or 10 seconds or 1 second. The guards have to go on. We do not want to get our fingers stuck in any of this. So let's put them on. Slide that over. Bob's your uncle. Good to go. All right. Remember this handsome guy? It's time to take him off. My personal key. Take off my personal lock. And there's that. We'll now turn the power on. Ooh. Okay, you see that yellow light. Now we're going to turn this power on. Ooh. You can notice that we have a hertz reading. Okay. Constant speed is going to run at the 60 hertz that the motor is rated for. Variable speed would be off of this. Okay. We're going to start with our constant speed. Ah, thing of beauty. So let's check the speed. Motor should be around 1700 according to the nameplate, and we get 1770 from our readings right here. So at the other end, because we used a bigger sheave, it should be a lot less. Let's measure it. We got 892. If we look at our motor nameplate, it'll give us an RPM of 1700. But when we actually measured it, we got an RPM of 1770. That's not uncommon to be a little bit off of the nameplate. That's when we were running at the constant hertz, constant 60 hertz. If you're going to use that VFD, you're going to get a variable frequency. So this is going to go up and down. Your speed's going to go up and down. But at the constant speed, this is somewhere in your range. Okay? So let's figure out some things about what we just built. We know that our driven and our driver pulleys, right? So what do we know about our driven and driver pulleys? Well, we just measured our driver RPM was 1770. We also know that the pitch diameter, the size of it, was 2 inches. Okay? What we know about the driven pulley, the pitch diameter was equal to 4 inches. What do we think if we were to measure our driven pulley? What do we think our speed would be? Pulley ratio is equal to pitch diameter driven over the pitch diameter of the driver, but also equal to the RPM of the driver over the RPM of the driven. So we go ahead and punch our numbers in. What we know, the driven is 4, the driver is 2, that's those, is equal to, we know the RPM of the driver is 1770, and we know nothing about what the driven is just yet. So when we do our math, 4x is equal to 2 times 1770. The RPM is 885. So now we figured out our RPM for our driven and driver sheaves that we have in place. What about our torque? I don't see any torque ratings. Well, if you go back to that motor nameplate and you look at that motor nameplate, you'll see that it has a horsepower of 3/8. It's a 3/8 horsepower motor, okay? But our equation for torque is torque equals the horsepower of the motor multiplied by 52, and then you divide that by your RPM. So let's go ahead and punch in some numbers, okay? Torque is equal to, okay, 3/8. If I were to do 3 divided by 8, that's going to be 0.375 multiplied by 52 over, what do we get? We had a measurement of 1700. We're gonna find it out for the driver first, I guess. We could figure it out for either, but let's just say we're going to use the driver and we're going to use 1770. And what does that give us? The torque is equal to 1969.5 over 1770. Torque is equal to 1.11 foot-pounds. Okay, now we could use this same formula and just plug in the 885, but let's go ahead and use the formulas that we know over here too. So that pulley ratio is equal to, we know the pitch diameter from over here was equal to 4/2, right? Driven pulley over the driver pulley. And we know that it's torque of the driven over the driver. So now we have 4/2. So we know that the torque that we just did of the driver is 1.11 foot-pounds. So 4.2 is equal to, we don't know, over 1.11. So now 2x is equal to 4 times 1.11. Okay, going to move up here. 2x is equal to 4.44. Now to get x alone, we have to divide that by 2. Divide that by 2. So our torque is going to be equal to 2.22 foot-pounds. That's what we're estimating it to be. All right, so we just did all this math to figure out what our torque would be with a 4-inch pulley on the driven and a 2-inch pulley on the driver. Let's just swap that around. What if we put this 2-inch on the driven side and the 4-inch on the driver's side? Okay, let's do that. So we know that our driven pulley has now a 2-inch pitch diameter. Okay, we know that our driver pulley has a new pitch diameter of 4 inches. Okay, now the speed won't change for the driver. It's going to be what it's going to be. So we're going to use that RPM of 1770 that we figured out before. All right, let's figure out what the new speed is for the driven. So pulley ratio equals the pitch diameter of the driven over the driver, but that also equals the RPM of the driver over the driven. Okay, so let's plug in our numbers. Our pitch diameter of the driven is 2/4. Okay. And our speed of our driver is 1770 over, we don't know. So 2x is equal to 4 times 1770. Now let's figure out the torque of the driven. So if we did this again, our pulley ratio is equal to the pitch diameter of the driven over the driver. Driven over the driver. And that is also equal to the torque of the driven over the driver. And in our first, over here, we know that our new driven is 2, our driver is 4 for our pitch diameter. So we have 2/4 or half, right? So half is equal to the torque of the driver is 0.556. Okay, so now we need to, we'll cross multiply. 2x is equal to 1 times 0.556. So we'll go ahead and we'll get that x by itself. So when you divide 0.556 by 2, you get. So why did we just do all that math? Well, it's just to understand that in our original setup, if we had that pulley that was 4 inches and we got a speed of 885 and a torque of this 1.11 foot-pounds, when you swap that out and you give that driven pulley a smaller pitch diameter, you've put the smaller pulley on, you more than doubled the speed, but you really cut down on the torque. So depending on what you need, do you need speed or do you need torque? You got to find that happy medium between your pulley ratios to get what you need.
How about we add a prawny brake? Why? Simple. In the real world, we don't just spin motors for fun. They have to drive a load. Now we're going to do it. We're going to add a brake to create a load so we learn and observe how that makes the motor react. Here's all the parts we need. Here's the drum. As you can see, it's just a big aluminum cylinder. It takes the friction from the belt. Okay. And you bolt it onto the shaft and you center that keyway. Tighten it down with Allen's. All right. Here's the friction belt or the friction strap. This is what causes that friction when it rubs against that drum and it simulates that load.
with this, it's put in place with these pins. Here's one pin that'll go through your plate, and then here on the other part is the other pin with this cotter pin key. All right, now's the belt tensioner. Okay, think of it as a clamp with an adjustment knob. It tightens the belt down, just like you're pulling on your belt strap. You can see the torque in pounds right here. We'll show you how it goes in a second. Now this brake drum is going to get hot once this friction keeps going, so we're going to need to cool it down. That's why it's kind of cupped, and we have this water here. We're going to fill it about a quarter of the way up when we go to do this, just to help keep this all cooled down. Alright, I got our Prawny brake drum. I'm going to attach it just like we said via the shaft and the keyway. So we'll put our keyway in. Remember, snug, not overly tight. Alright, I'm going to line that up a little bit with the bottom. Slide that in till it don't go no more. Okay, just that easy. And then I'm going to use our handy dandy Allens. Tighten down. Now it's time to put on our friction strap. So I'm going to take the first pin out and the cotter pin, set it aside. I'm going to take this guy right here, and you'll see this slot right here that's made to put this into here. And then we take this pin and we put it on from underneath. Center it on that, and then we pull it tight. Okay, let's take our tensioner, loosen it up, slide it up through the table. And you can do it. All right, this is where we take our pin from earlier. Okay, I'm gonna take this. We're gonna loosen it all the way up in order to reach. All right, start this. Insert our cotter pin. Bob's your uncle. There she is. Now you can notice as I turn this screw, I'm going to bring it first down to 0. But I can continue to turn this screw and draw that belt tighter and tighter and tighter, creating a friction. Could create a lot of heat. So we're going to go ahead and put about 1/4 inch of water inside that drum to help keep that cool while it's running. Let's go ahead and start this motor with our Prawny on it. I want to be checking the hertz, driving it all the way to the 60 hertz that the motor's rated for. It's now running. Let's check the amperage. It's running at 1.5 amps. Why do we need to know that? Well, when we start to crank up the tension on this tensioner belt, as we turn the knob, you can see we're turning the knob to the right. And as we turn that knob to the right, we're putting drag on this belt, which is getting tighter and tighter around that Prawny drum, which will cause the amperage to go up because the motor has to work harder to maintain that 60 hertz. And for speed too, the speed will stay the same, but as we tighten this down, it's just going to have to work harder. Still 60 hertz, still 1650 RPM, but now we're at 1.8 amps. And it's going to continue to go up as we tighten that down. We were at 1.8 amps, and as I tighten that down, you can see that torque on that belt is tightening down, right, on that tensioner belt. It's tightening down, tightening down, tightening down. We're now at same speed, 1650, just has to work harder. We're at 2 amps. That's a lot more amperage. 2 amps is about the limit for this thing. If we go ahead and we turn it down any more than that, it's probably going to overload, which means it's just working too hard. Let's see. So we're at 1650. Going to grab that knob, turn it down. We're about at the end of the bell here, which means we're putting on as much torque as we probably should. And, oh, look, overload. It kicked out. It's too much amperage. It worked too hard.
All right, so what did we learn today? Well, today we mounted and leveled a motor. We mounted and leveled the shaft and mounted the sheaves. We learned how to do a proper alignment. We learned how to calculate speed and torque based off the pulley size. We learned how to use a prony brake, which essentially showed us how a real-world application affects a motor's amperage and speed. And you know what else we did? We did a great job. Stay tuned if you want help with Skill 2 from your lab. Today we're going to be using these formulas to work on our skills in our labs. We're mostly going to be focusing on our belt-driven formulas, which include formulas for our pulley ratios in RPM, torque, and the pitch diameters. Question number 1 wants us to figure out the pulley ratio when the driver pulley has a pitch diameter of 4 and the driven pulley has a pitch diameter of 2.5. Well, our equation for pulley ratio is equal to the pitch diameter of the driven over the pitch diameter of the driver. We know that the driver pulley has a pitch diameter of 4, and we know the driven pulley has a pitch diameter of 2.5. Okay, so if we divide 2.5 by 4, our pulley ratio is equal to 0.625. Question number 2 wants us to calculate the pulley ratio when the driven pulley pitch diameter is equal to 6, but the driver pulley pitch diameter is equal to 3. So for question number 2, pulley ratio is again equal to the pitch diameter of the driven over the pitch diameter of the driver. In our case, we know that the driven pulley has a pitch diameter of 6 and the driver pulley has a pitch diameter of 3. So our new pulley ratio is equal to 2. 3 wants us to calculate the pulley ratio when our driver pulley has a pitch diameter of 4 and our driven pulley has a pitch diameter equal to 4. Okay, that seems pretty simple. I always like to keep writing our formula down over and over again, and that way it gives me that practice. It builds it into my head. I will always know the formula. So again, our formula is the pulley ratio is equal to the pitch diameter of the driven pulley over the pitch diameter of the driver pulley. Okay, and we know that in our case the pitch diameter the driven is 4, the driver is 4, so our pulley ratio is equal to 1. Question number 4 wants us to figure out the pulley ratio when our driver pulley is a pitch diameter of 8 and the driven pulley has a pitch diameter of 2. Okay, pulley ratio equals the pitch diameter of the driven over the driver. Driver is 8, the driven is 2, so our new pulley ratio is equal to 1/4 or 0.25, however you want to write it. Skill number 2 is going to want us to start calculating the RPM. In this question for number 1, it wants us to calculate the RPM for the driven shaft speed. We know that our driven pulley has a pitch diameter of 4 and our driver pulley has a pitch diameter of 2. We know the driver has a torque of 200 and a speed of 1750. So pulley ratio is equal to pitch diameter of the driven over the pitch diameter of the driver.
but it's also equal to RPM of the driver over the RPM over the driven. Okay, so let's figure this one out first. We know that our driven has a pitch diameter of 4 and our driver pulley has a pitch diameter of 2. Okay, awesome. Now we also know that our RPM of our driver is equal to 1750 over the unknown. So when we cross multiply, we'll end up getting 4x is equal to 2 times 1750. Okay, 4x is equal to. So now it wants us to calculate the torque. Pulley ratio is equal to the torque of the driven over the torque of the driver. Okay, we know our pulley ratio from question before was our pitch diameter was 4 over 2. Okay, and that was equal to, and we know our torque of the our torque of the driver pulley is 200 foot-pounds. So that's x over 200. So 2x, because we're going to cross multiply, is equal to 800. X is, so we're going to divide that by 2. Divide that by 2. X is going to be equal to 400 foot-pounds. Question number 3 wants us to calculate the driver shaft speed of the belt for these two pulleys. What we know is our driven pulley has a pitch diameter of 6, our driver pulley has a pitch diameter of 4. Driven has 800 RPM and 300 foot-pounds torque. Let's just write these things out and make things a little bit easier this time. So question number 3, okay, our driven pulley has pitch diameter of 6, a torque of 300 foot-pounds, and a speed of 800 RPM. Our driver pulley has a pitch diameter equal to 4. That's all we know at the moment. So let's go ahead and do our math. We know that the pulley ratio is equal to the pitch diameter of the driven over driver. Pitch diameter over driver. Okay, in our case, the driven is 6 over 4, which can also be reduced to 3 over 2, right? So pulley ratio is equal to 3 over 2, but it's also equal to the speed, or the we'll do RPMs, RPM of the driver pulley over the driven, RPM driven. Okay, we know that the driven pulley has an RPM of 800. Okay, so 3 over 2 is equal to x over 800 RPM. So then when we cross multiply, 2x is equal to 3 times 800. So 2x is equal to 2400. Okay, if we divide that by 2, x is equal to 1200 RPM. For question number 4, we're using that same pulley setup, but it wants us to figure out the foot-pounds, the torque, which we know on the driven pulley was 300. So how are we going to calculate? Well, our pulley ratio we've already figured out was 3 over 2. And we know our torque, which pulley ratio also equals the torque of the driven over the driver. Driven pulley over the torque
of the driver pulley. Okay. We know that our torque of the driven pulley is equal to 300. So 3 over 2 is equal to 300 over x. Okay. So when we cross multiply, 3x is equal to 2 times 300. 3x is equal to 600. So then let's divide that by 3. Divide that by 3. X is equal to 200 foot-pounds. Question number 5. All right. Question number 5 doesn't show us any nice visuals. It just tells us the data that we need. So it tells me that my driver pulley has a torque, or let's start with pitch diameter. It has a pitch diameter equal to 2 inches. It has a torque of 200 foot-pounds and a speed of 3,500 RPM. Our driven pulley, all we know is the pitch diameter is equal to 8. So knowing that, we're going to calculate the speed first. So pulley ratio is equal to our pitch diameter of the driven over the driver, okay, which is also equal to the speed, or let's do RPM of the driver over the RPM of the driven. So let's put our numbers in and see what that equals. The pulley pitch diameter of the driven is equal to 8. The pitch diameter of the driver is equal to 2. Okay, so that's also equal to what? 4 over 1. And then what we have for the driver, for the RPM, is 3,500. Okay, we don't know the RPM of the driven just yet. So when we cross multiply these right here, we have 4x is equal to 3,500. When we divide that by 4, x is going to give us a speed of 875 RPM. It wants us to go ahead and figure out the torque. So we know that pulley ratio is equal to the pitch diameter of the driven over the driver, but we also know that that's equal to the torque of the driven over the driver. From question number 1, we know that our pulley ratio is equal to 4 over 1. That's right here. And we know our torques. So our torque of our driver is equal to 200 foot-pounds. But we don't know the torque of the driven yet. So when we cross multiply, x equals 4 times 200. X equals 800 foot-pounds. There we go. 7 gives us a whole new set of sheaves. So let's go ahead and write what we need to know down. We have a driver pulley which has a pitch diameter of 3.5 inches. It has a torque of 400 foot-pounds and a speed of 1,000 RPM. That's inches. We have a driven pulley, but all we know is the pitch diameter is equal to 2. Now, if we go ahead, we can write all our equations out right now if we want. Our pitch diameter
is equal to, our pulley ratio is equal to our pitch diameter of the driven over the driver. Driven over the driver, which is equal to the speed of the driver over the speed of the driven, which is also equal to the torque of the driven over the torque of the driver. But question number 7 is only interested in knowing the RPM. So we're going to start out with this pulley ratio. We know both the driven and driver inch diameter of the pitch diameter of these. So the pitch diameter of the driven is 2 and the driver is 3.5. Okay, now we know the speed because question number 7 wants us to know the speed. We know the speed of the driver is 1000 RPM, but we don't know the speed of the driven yet. When we cross multiply, we have 2x is equal to 3.5 times 1000. So question number 8 wants us to figure out that same sheaves, but you figure out the torque for them. Okay, so we noticed here that our pulley ratio is equal to 2 over 3.5. Okay, and then we know that that's also equal to the torque of the driven over the torque of the driver. Okay, so 2 over 3.5 is equal to the torque of the driven, which is, we don't know. The torque of the driver is 400. So 3.5x 0.5x is equal to 2 times 400. 3.5x is equal to 800. So when we divide that out, we got to divide to get our x alone. Okay, so then the x would be equal to 228 foot-pounds. There's your answer for number 8.